1 billion years is not a future we instinctively understand. It is not a date that fits naturally into human thinking, nor a span of time that can be felt through memory or imagination in the way decades or centuries can. It exists far beyond lived experience, beyond recorded history, and beyond the rhythm of civilizations. To move 1 billion years into the future is to leave behind familiar measures of change and enter a domain where time itself behaves differently, where processes unfold not in moments or generations, but in vast, almost imperceptible transitions. Human history, from the earliest tools to the present moment, occupies only a fraction of this scale. Entire empires rise and disappear in less than a blink when compared to a billion-year timeline. Languages form, transform, and vanish. Our continents drift by distances measured in kilometers, not meters. Species appear, evolve, and quietly fade. When viewed from this distance, the present becomes a thin surface layer atop a much deeper story. To understand the future of Earth, the solar system, and the universe itself, it is necessary to slow perception down to match the pace of cosmic change. In deep time, nothing happens suddenly. Even the most dramatic transformations unfold gradually, guided by physical laws that operate continuously and without urgency. Gravity does not hurry. Nuclear reactions do not rush. Orbits repeat patiently, millions of times, before their effects become noticeable. The concept of deep time was once difficult, even for scientists to accept. Early human perspectives assumed a young Earth and a static sky, when where stars and planets existed primarily as unchanging backdrops. It was only through careful observation, geology, and astronomy that a different reality emerged. Rocks recorded histories older than any myth. Stars revealed life cycles far longer than civilizations. The universe itself showed signs of an age measured not in thousands, but in billions of years. 1 billion years into the future, the familiar world does not vanish abruptly. It transforms. Earth does not disappear in fire or collapse into darkness. Instead, it changes slowly, responding to forces that are already at work today. The sun continues to shine, but not in exactly the same way. The moon continues to orbit, but not at the same distance. The planet continues to turn, but under subtly altered conditions. The future is shaped not by sudden events, but by accumulation. Small changes compound over immense spans of time. A fraction of a percent increase in solar brightness becomes decisive when sustained for hundreds of millions of years. A few centimeters of lunar drift each year become thousands of kilometers. The steady escape of atmospheric gases becomes irreversible. Deep time magnifies what seems insignificant in the present. To travel forward 1 billion years is to observe the consequences of stability. The laws of physics do not change. The constants that govern matter, energy, and motion remain fixed. What changes is the outcome of their persistence. Given enough time, even gentle forces reshape entire worlds. At the beginning of this journey, Earth is still recognizable. The sun still rises, oceans still exist, and the planet remains firmly bound to its star. There is no dramatic boundary that marks the departure from the present. Instead, there is continuity. The future grows directly out of the present, inheriting its momentum, its composition, and its constraints. The sun, at the center of this story, has already lived for over 4 billion years. It is not a static object, but a dynamic system powered by nuclear fusion. At its core, hydrogen atoms merge to form helium, releasing energy that travels outward and eventually reaches Earth as light and heat. This process is steady and reliable, but it is not perfectly constant. Over time, the balance of elements in the Sun's core changes, subtly altering the energy it produces. 1 billion years from now, the Sun will be slightly brighter than it is today. The increase will not be dramatic on human timescales, but it will be profound on planetary ones. This gradual brightening is one of the most important drivers of Earth's long-term future. It does not require catastrophe. It requires only patience. Earth itself is not passive in this process. The planet responds dynamically to changes in energy input. Its atmosphere, oceans, and surface form a complex system that seeks balance. When energy increases, feedback mechanisms activate. Some amplify the change, while others resist it. Over short timescales, this system can appear stable. Over deep time, stability gives way to transformation. The future of Earth is therefore not a single event, but a sequence of stages. Each stage flows into the next, shaped by interactions between solar radiation, atmospheric chemistry, geological cycles, and biological activity. None of these processes act alone. Together, they form a network of cause and effect that unfolds slowly but relentlessly. Moving 1 billion years into the future also requires letting go of familiar markers. Political boundaries, cities, and cultures have no relevance at this scale. Even species are temporary. What remains meaningful are larger patterns, planetary motion, stellar evolution, and the behavior of matter under consistent physical laws. This perspective does not diminish the present. Instead, it places it within a broader context. The present becomes one moment in a long continuum rather than a fixed point of significance. Earth's current conditions are neither permanent nor accidental. They are a phase, sustained by a particular balance of forces that will eventually shift. As this journey begins, the goal is not to predict every detail of the future, but to understand its direction. Science does not provide exact timelines for every outcome, but it does offer boundaries. It tells us what must happen, what may happen, and what cannot happen, given what is already known about the universe. 1 billion years into the future, Earth will still exist. The solar system will still be intact. The Milky Way will continue its slow rotation. The universe will remain governed by the same principles that operate today. What changes is not the framework, but the expression of that framework over time. Deep time reveals a universe that is neither chaotic nor static, but gradual. Change is the rule, but it proceeds at a pace that is easy to overlook. When viewed from the present, the future seems distant and abstract. When viewed from deep time, the present itself becomes fleeting. And this is the scale on which planets live, stars age, and galaxies evolve. To move forward 1 billion years is not to witness an ending, but to observe a continuation, a slow unfolding of processes already underway, guided by laws that do not pause, but also do not rush. From this foundation, the story of Earth's future can begin, not with drama or speculation, but with the quiet certainty of physics and time working together. The sun appears constant from day to day, rising and setting with dependable regularity, delivering warmth and light in a pattern so familiar that it is easy to mistake it for permanence. Yet beneath this apparent stability lies a slow, irreversible process of change. The sun is not a fixed source of energy. It is an evolving star, governed by physical laws that ensure its behavior today will not be identical to its behavior 1 billion years from now. At its core, the sun is a sphere of plasma held together by gravity. The immense weight of its outer layers compresses the core to temperatures exceeding 15 million degrees. Under these conditions, Hydrogen nuclei move rapidly enough to overcome their natural repulsion and fuse together. This fusion process converts hydrogen into helium, releasing energy according to the relationship between mass and energy described by physics. The energy produced at the core does not travel outward instantly. Instead, it migrates slowly through the sun's interior, taking thousands of years to reach the surface. This slow journey matters because it smooths out fluctuations. The sun does not flicker or surge dramatically. Its output is remarkably steady on short timescales. But on the scale of hundreds of millions of years, the gradual conversion of hydrogen into helium changes the internal balance of the star. As helium accumulates in the core becomes denser. Gravity responds to this increased density by compressing the core further, raising its temperature and accelerating the fusion process. This feedback loop leads to a slow but measurable increase in the sun's energy output. Astronomers estimate that the sun becomes brighter by roughly 10% every billion years. This number may appear modest, but for a planet like Earth, which exists within a delicate balance of incoming and outgoing energy, even small changes have profound consequences. The sun's evolution follows a path common to many stars of similar mass. When it was born from a cloud of gas and dust, ignited when gravity compressed its core to fusion temperatures, and entered a long phase of relative stability known as the main sequence. During this phase, the sun spends the majority of its life converting hydrogen into helium in a controlled and predictable manner. 1 billion years into the future, the sun will still be in this main sequence phase. It will not yet have expanded into a red giant or begun the dramatic transformations associated with stellar old age. From a stellar perspective, the sun will still be considered middle-aged. Yet even within this stable phase, evolution continues. As the core's composition changes, the sun's structure adjusts. The increased fusion rate produces more energy, which pushes outward against gravity. To maintain equilibrium, when the outer layers of the sun expand slightly, this expansion lowers the density of the outer regions, while the core continues to contract. The result is a star that is both brighter and marginally larger than it is today. This increase in brightness translates directly into greater energy received by the planets. Earth, in particular, will experience a higher average input of solar radiation. The change will not be sudden or dramatic within a single generation. It will unfold slowly, unnoticed by any individual observer, but it will steadily shift the planet's climate system. The sun's quiet evolution highlights an important aspect of cosmic change. Not all transformative processes are violent or explosive. Some of the most consequential changes occur through stability itself. The sun does not need to flare catastrophically to alter Earth's future. Its steady, predictable behavior is sufficient. In the present era, Earth's climate is regulated by a balance between solar input and the planet's ability to reflect and radiate energy back into space. Clouds, ice, oceans, and atmospheric gases all play roles in maintaining this balance. As solar brightness increases, this equilibrium is gradually pushed toward a warmer state. Over millions of years, small shifts accumulate. Average global temperatures rise, ice coverage decreases, ocean circulation patterns adjust. None of these changes are isolated. Each interacts with the others, creating feedback loops that can either amplify or dampen the initial warming. The sun's evolution also affects the chemistry of Earth's atmosphere. Higher energy input increases the rate of chemical reactions in the upper atmosphere. Ultraviolet radiation becomes slightly more intense, influencing the behavior of molecules such as water vapor, carbon dioxide, and oxygen. These changes further modify the planet's energy balance. Beyond Earth, the sun's increasing luminosity influences the entire inner solar system. Mercury and Venus receive even greater amounts of energy, accelerating processes that have already transformed them into extreme environments. Mars, though colder and thinner in atmosphere, also experiences subtle changes as solar radiation increases. Despite these shifts, the Sun remains remarkably reliable. It does not vary unpredictably. Its evolution follows a trajectory that can be modeled and understood with confidence. And this predictability allows scientists to project Earth's long-term future with a degree of certainty unavailable in many other domains. The concept of stellar evolution emphasizes that stars are not static backdrops for planetary systems. They are active participants in shaping planetary environments. The fate of a planet is inseparable from the fate of its star. Over deep time, this connection becomes increasingly evident. 1 billion years into the future, the Sun will still appear familiar in the sky of Earth, assuming an observer could stand there. It will still be a yellow-white disk, still rising and setting. Yet its influence will be subtly stronger, its energy more insistent. The difference lies not in appearance, but in consequence. This gradual brightening sets the stage for the transformations that follow. It initiates a chain of events that will reshape Earth's surface, atmosphere, and biosphere. These changes are not the result of chance or external catastrophe. They arise from the natural progression of a star doing what stars do. The Sun's quiet evolution serves as a reminder that the universe does not require drama to produce profound outcomes. Consistency, when sustained over immense spans of time, becomes a powerful force. The same nuclear reactions occurring in the Sun today will continue tomorrow, and the day after, and for millions of years beyond. Their cumulative effect defines the future. Understanding this process allows us to view the future not as an unknown void, but as an extension of the present. The Sun's behavior 1 billion years from now is already determined by the conditions that exist today. Thus, its path is written into its mass, composition, and internal structure. As this journey through deep time continues, the Sun remains the central driver of change for Earth. Its slow evolution provides the energy that powers planetary processes and the gradual shift that moves Earth from one state to another. In the next stage of this story, the focus turns more directly to how Earth responds to this increasing energy, and how the planet's climate system begins to move beyond the conditions that have supported life for billions of years. As the Sun's energy output increases, Earth does not respond all at once. The planet absorbs the change gradually, distributing additional heat through systems that evolved under far more stable conditions. At first, the effects are subtle. Average temperatures rise slowly, measured not in dramatic shifts, but in fractions of degrees spread across millions of years. These changes are small enough to escape notice in the short term, yet persistent enough to alter the planet's long-term trajectory. Earth's climate is regulated by a balance between incoming solar radiation and outgoing heat. This balance is maintained through a network of interacting components: the atmosphere, the oceans, the cryosphere, and the biosphere. When the Sun brightens, this balance is disturbed. More energy enters the system than leaves it, and Earth must adjust. The adjustment does not follow a straight line. It unfolds through feedbacks, delays, and thresholds. One of the earliest responses to increased solar energy is the warming of the oceans. Water has a high capacity for storing heat, which allows the oceans to absorb excess energy and slow the rate of atmospheric warming. This buffering effect delays immediate consequences, creating the illusion of stability. But stored heat does not disappear. Over time, warmer oceans release more energy back into the atmosphere, reinforcing the initial warming. As temperatures rise, evaporation increases. More water vapor enters the atmosphere, and this has important consequences. Water vapor is itself a powerful greenhouse gas. It traps heat by absorbing infrared radiation emitted from Earth's surface and re-radiating it back downward. As water vapor concentrations increase, the atmosphere becomes more effective at retaining heat, amplifying the warming caused by the brighter sun. This process illustrates a positive feedback loop. An initial increase in temperature leads to more water vapor, which leads to further warming, which in turn leads to even more water vapor. Such feedbacks do not create immediate runaway effects, but over deep time they push the climate system steadily toward a warmer state. Ice plays a crucial role in regulating Earth's temperature by reflecting sunlight back into space. Large ice sheets and polar ice caps act as mirrors, reducing the amount of energy absorbed by the planet. As temperatures rise, ice coverage decreases. Darker land and open ocean surfaces replace reflective ice, absorbing more sunlight. This change further increases warming, reinforcing the trend already underway. The retreat of ice alters not only temperature but also sea level. As glaciers melt and polar ice diminishes, water redistributes across the planet. Our sea levels rise slowly, but persistently. Coastlines shift. Shallow seas expand inland. Over millions of years, these changes reshape continents and influence ocean circulation patterns. Ocean currents are driven by differences in temperature and salinity. As polar regions warm and ice melts, fresh water enters the oceans, altering salinity gradients. These changes affect the global circulation system that transports heat from equatorial regions toward the poles. Subtle shifts in circulation can have wide-ranging effects, influencing climate far from their point of origin. Earth's atmosphere also evolves in response to increased solar radiation. Higher energy input enhances chemical reactions in the upper atmosphere, including those involving water vapor, carbon dioxide, and oxygen. Ultraviolet radiation breaks apart molecules more efficiently, changing the balance of gases over time. These chemical changes further modify how energy moves through the atmosphere. Carbon dioxide, another key greenhouse gas, responds indirectly to rising temperatures. Warmer oceans hold less dissolved carbon dioxide, allowing more of it to escape into the atmosphere. At the same time, weathering processes on land may accelerate, drawing carbon dioxide out of the atmosphere and storing it in rocks. The balance between these opposing effects determines how carbon dioxide levels change over long timescales. Biological activity also plays a role. Plants absorb carbon dioxide through photosynthesis, influencing atmospheric composition. However, as temperatures rise and environments shift, ecosystems change. Some regions become less hospitable to plant life, reducing the biosphere's capacity to regulate atmospheric gases. Over deep time, biological feedbacks weaken as environmental conditions move beyond the range that supports complex life. The combined effect of these processes is a gradual but persistent warming trend. Earth does not tip suddenly into an uninhabitable state. Instead, it moves through a series of transitional climates, each one warmer than the last. What defines these transitions is not a single factor, but the cumulative impact of many small changes reinforcing one another. Clouds introduce additional complexity. Depending on their type, altitude, and distribution, clouds can either reflect sunlight or trap heat. Changes in temperature and atmospheric composition alter cloud formation patterns. Some cloud changes may temporarily offset warming, while others may enhance it. Over millions of years, the net effect tends toward amplification rather than stabilization. As the sun continues to brighten, the average surface temperature of Earth rises beyond the range that supported stable climates in the past. Regions near the equator experience increasing heat stress. Tropical environments expand poleward. Areas that were once temperate become warmer and drier. Polar regions, once dominated by ice, transition toward more moderate conditions, at least temporarily. Rainfall patterns shift as atmospheric circulation responds to new temperature gradients. Some regions receive more precipitation, while others become increasingly arid. These changes reshape landscapes slowly, influencing erosion, sediment transport, and soil formation. Yet rivers alter their courses. Deserts expand and contract over geological timescales. Earth's rotation and axial tilt remain largely unchanged during this period, preserving seasonal cycles. However, the expression of seasons changes as baseline temperatures rise. Winters become milder, summers warmer. The contrast between seasons diminishes in some regions and intensifies in others, depending on local geography and circulation patterns. The planet's response to a brighter sun highlights the interconnectedness of Earth systems. No single component determines the outcome. Instead, the future climate emerges from the interaction of physics, chemistry, and biology operating together over immense spans of time. Each system responds according to its own rules, yet none operates in isolation. Importantly, the changes unfolding on Earth are not driven by chance events. They are the predictable result of increased energy input combined with known feedback mechanisms. While uncertainties remain regarding exact timelines and regional outcomes, the overall direction of change is clear. A brighter sun leads to a warmer Earth. 1 billion years into the future, Earth's climate will have moved well beyond the conditions that characterize the present. The planet will still possess an atmosphere and oceans, but the balance that maintained long-term habitability will be under increasing strain. The processes that once stabilized climate begin to lose effectiveness as thresholds are approached. This stage of Earth's future is defined not by collapse, but by transition. The planet adjusts continuously, seeking new equilibria under altered conditions. Life, geology, and atmosphere respond in ways shaped by their own limits and capacities. Some systems adapt, others weaken. None remain unchanged. The gradual warming of Earth under a brighter sun sets the stage for more profound transformations yet to come. It initiates a chain of events that will eventually reshape the planet's surface, alter its atmosphere, and redefine the boundaries of habitability. These outcomes are not sudden, but they are inevitable, given enough time. As the journey through deep time continues, attention turns to one of the most critical consequences of this warming: the long-term stability of Earth's oceans. Water, central to the planet's climate and life, becomes increasingly vulnerable as temperatures rise. The next stage explores how this defining feature of Earth begins to change under the persistent influence of a brighter sun. For most of Earth's history, the oceans have acted as a stabilizing force. They absorb heat, regulate climate, support chemistry, and provide a medium in which life can persist even as surface conditions fluctuate. Over deep time, however, this stability depends on limits. As solar energy continues to increase, the mechanisms that once preserved Earth's oceans begin to weaken, and the long-term balance that keeps water liquid at the surface starts to shift. The warming initiated by a brighter sun does not immediately eliminate the oceans. Instead, it alters the way water behaves within the climate system. Higher temperatures increase evaporation rates across the planet. More water transitions from liquid to vapor, entering the atmosphere in greater quantities. At first, this change is gradual and uneven, affecting warmer regions more strongly than cooler ones. As atmospheric water vapor increases, its greenhouse effect becomes more pronounced. Water vapor absorbs infrared radiation efficiently, trapping heat that would otherwise escape into space. This process intensifies surface warming, which in turn accelerates evaporation. The result is a feedback loop in which rising temperatures and increasing water vapor reinforce one another over millions of years. This feedback does not require extreme conditions to begin. It emerges naturally once the atmosphere contains enough water vapor for its greenhouse effect to dominate other regulatory processes. Over time, the balance between incoming solar radiation and outgoing heat shifts decisively toward warming. As the atmosphere grows warmer and more humid, clouds become more prevalent at higher altitudes. High-altitude clouds tend to trap heat rather than reflect sunlight, further contributing to warming. While some low-altitude clouds may reflect solar radiation and provide temporary cooling, their influence weakens as overall temperatures rise and atmospheric circulation patterns change. Eventually, Earth approaches a climatic threshold known as a moist greenhouse state. In this condition, water vapor becomes a dominant component of the upper atmosphere. The stratosphere, which today is relatively dry, begins to fill with water molecules carried upward by vigorous convection. This change has critical consequences for the planet's long-term water retention. In the upper atmosphere, water molecules are exposed to ultraviolet radiation from the sun. This radiation breaks water apart into hydrogen and oxygen. The lighter hydrogen atoms move rapidly and can escape Earth's gravitational pull, drifting into space. Oxygen, being heavier, remains behind, potentially reacting with surface materials or accumulating in the atmosphere. This process, known as atmospheric escape, is slow but irreversible. Each hydrogen atom lost represents a tiny fraction of Earth's total water inventory. Over short timescales, the loss is negligible. Over hundreds of millions of years, it becomes significant. Over 1 billion years, it reshapes the planet. As hydrogen escape continues, the total amount of water on Earth gradually decreases. Us oceans shrink not through sudden disappearance, but through persistent thinning. Sea levels fall as water is lost to space faster than it can be replenished through geological processes. At the same time, rising temperatures place stress on the remaining liquid water. Warmer oceans dissolve less carbon dioxide, altering atmospheric composition. Changes in salinity and circulation disrupt the ocean's ability to transport heat and nutrients. The ocean's role as a climate buffer weakens. As continents continue to drift, geological processes such as plate tectonics persist, but their interaction with the climate changes. Weathering rates on land may increase initially as higher temperatures and precipitation accelerate chemical reactions. Over time, however, as water availability decreases and landscapes become drier, weathering slows. The planet's capacity to regulate atmospheric carbon dioxide through rock formation diminishes. The oceans also play a central role in biological productivity. Phytoplankton at the surface form the base of marine food webs and contribute significantly to oxygen production. As surface temperatures rise and nutrient circulation is disrupted, marine ecosystems decline. Productivity falls. Oxygen generation decreases. This decline does not occur uniformly. Some regions remain productive longer than others. Deep ocean environments persist even as surface conditions worsen. Life adapts where it can, retreating into niches that offer relative stability. Yet the overall trend is toward reduction rather than expansion. As water vapor becomes more abundant in the atmosphere, precipitation patterns change. A rainfall becomes more intense in some areas and nearly absent in others. Extreme events become more common on geological timescales. Rivers carve deeper channels, then dry up as water availability decreases. Lakes shrink and vanish. Inland seas retreat. Eventually, Earth's climate crosses a more decisive threshold: the runaway greenhouse state. In this regime, surface temperatures rise to levels at which liquid water can no longer remain stable over large areas. Evaporation outpaces condensation. Clouds fail to reflect sufficient sunlight to offset warming. The feedback loop accelerates. In a runaway greenhouse, the oceans do not boil away in a single dramatic event. Instead, they evaporate progressively. The atmosphere grows thick with water vapor, becoming dense and opaque. Surface temperatures rise further as the greenhouse effect intensifies. This process is not speculative. It is believed to have occurred on Venus early in its history. Venus, once possibly home to liquid water, lost its oceans through a similar sequence of events driven by solar radiation and atmospheric feedbacks. Earth, given enough time and a brightening sun, follows a comparable path. As the oceans recede, Earth's surface undergoes profound transformation. Sediments once deposited by water are exposed. Salt flats expand. Chemical weathering slows dramatically as liquid water becomes scarce. The planet's surface begins to resemble a desert world, marked by vast dry basins and mineral-rich plains. The loss of oceans also alters Earth's rotational dynamics slightly. The redistribution of mass affects how the planet spins, though these changes are subtle and unfold over long timescales. Tides weaken as water volume decreases, further reducing the Moon's influence on Earth's surface processes. Atmospheric composition shifts as water loss continues. Oxygen produced by water breakdown may accumulate temporarily, but without biological replenishment and with increasing surface reactions, it does not remain stable. The atmosphere becomes dominated by gases less effective at supporting life. Despite these dramatic changes, Earth does not become inactive. Geological processes continue beneath the surface. Volcanism persists, releasing gases from the mantle. Tectonic motion reshapes continents slowly. The planet remains dynamic, even as surface conditions grow increasingly hostile. The end of stable oceans marks a turning point in Earth's history. Water, once the defining feature of the planet, becomes a limited and precious component of its environment. This transition fundamentally alters Earth's identity, moving it away from the conditions that supported complex life for billions of years. This stage of Earth's future unfolds gradually, without sudden catastrophe. There is no single moment when the oceans vanish. Instead, there is a long interval during which water becomes less reliable, less abundant, and less central to planetary processes. As this transformation progresses, the biosphere responds in predictable ways. Life retreats into environments where liquid water persists longest. Extremes become the norm. Adaptation replaces diversity. Eventually, even these refugees become unsustainable. The story of Earth's oceans is not one of sudden loss, but of gradual change driven by consistent physical forces. The same sun that once made Earth habitable slowly reshapes it into something else. The outcome is not a failure of balance, but the natural evolution of a planet under a changing star. With the oceans no longer stable, Earth enters a new phase of its existence. The planet continues forward in deep time, carrying the imprint of its watery past, even as liquid water fades from its surface. The next stage of this journey follows the consequences of this transition for life itself, as biological systems confront conditions increasingly unlike those under which they evolved. Life on Earth has always been shaped by limits. Temperature, water availability, chemical balance, and energy flow define where organisms can survive and how complex ecosystems can become. But as Earth's oceans lose stability and surface conditions shift steadily toward higher temperatures and increasing dryness, these limits tighten. Life does not vanish suddenly. It recedes, adapts, simplifies, and ultimately yields to environments no longer capable of sustaining complexity. In the early stages of this transition, many forms of life persist despite growing stress. Forests retreat toward higher latitudes and elevations where temperatures remain relatively moderate. Tropical ecosystems, once rich with diversity, become increasingly hostile as heat and humidity exceed the tolerance of many organisms. Species distributions shift gradually, following the narrowing corridors of habitable climate. Marine life responds first to changes in ocean chemistry and circulation. As surface waters warm and stratify, nutrient mixing declines. Phytoplankton populations decrease, reducing the foundation of marine food webs. Fish and other complex marine organisms decline as oxygen levels drop and food becomes scarce. Deeper ocean regions, insulated from surface extremes, remain habitable longer. But even these refugees are affected as circulation weakens. On land, plant life faces increasing challenges. Higher temperatures accelerate respiration rates, increasing water demand. As rainfall patterns become more erratic and overall water availability declines, many plants struggle to maintain hydration. Photosynthesis becomes less efficient under heat stress, reducing growth and reproduction. Over time, large plants and trees disappear from most regions, replaced by smaller, more resilient forms. Animals dependent on complex food chains begin to decline as ecosystems lose stability. Large-bodied organisms are particularly vulnerable due to their higher energy requirements. Mammals, birds, and reptiles experience widespread extinction as suitable habitats fragment and vanish. The planet's biosphere simplifies, losing diversity and complexity as environmental constraints tighten. Microbial life proves more resilient. Bacteria and archaea occupy a wide range of environments and possess metabolic pathways capable of functioning under extreme conditions. As complex life declines, microbial ecosystems expand into newly available niches. Hot springs, salt flats, deep subsurface environments, and isolated water pockets become centers of biological activity. Photosynthetic organisms also undergo transformation. While plants and algae decline, some photosynthetic microbes persist longer, adapting to higher temperatures and altered light conditions. Over time, however, even photosynthesis becomes increasingly difficult as water availability diminishes and atmospheric composition changes. As oceans thin and atmospheric water vapor escapes to space, the biosphere's ability to regulate planetary conditions weakens. Life has long played a role in shaping Earth's atmosphere, stabilizing oxygen and carbon dioxide levels through biological cycles. As biological productivity declines, these cycles slow and eventually break down. Oxygen levels fluctuate as the balance between production and consumption shifts. Without abundant photosynthetic organisms, oxygen is no longer replenished at rates sufficient to offset chemical reactions with surface rocks and volcanic gases. Over long timescales, atmospheric oxygen decreases, whilst removing a key requirement for complex aerobic life. The loss of oxygen does not mark an immediate end to life. Many microorganisms thrive in low oxygen or oxygen-free environments. Anaerobic metabolisms, which do not rely on oxygen, become increasingly dominant. These life forms resemble some of the earliest organisms to inhabit Earth, drawing energy from chemical gradients rather than sunlight. Earth's biosphere thus begins to resemble its distant past. Complexity gives way to simplicity. Diversity narrows. The planet transitions from a world rich in interacting ecosystems to one dominated by isolated, specialized communities adapted to harsh conditions. geographical isolation becomes increasingly important. Life persists longest in regions where liquid water remains available, even intermittently. Underground environments, shielded from surface heat and radiation, provide stable conditions for microbial ecosystems. Pores in rock, deep aquifers, and geothermal systems become sanctuaries for the last remaining life. These subsurface ecosystems are sustained by chemical energy released from interactions between water and rock. Reactions involving iron, sulfur, and hydrogen provide metabolic fuel independent of sunlight. Such environments change slowly and remain relatively insulated from surface extremes, allowing life to persist long after surface habitability declines. As surface temperatures continue to rise, even these refugees become strained. Water becomes increasingly scarce. Chemical gradients weaken. Energy sources diminish. Life adapts by slowing metabolic rates, entering dormant states, and relying on long-lived molecular repair mechanisms to survive extended periods of stress. The pace of biological activity slows dramatically. Reproduction becomes infrequent. Evolutionary change continues, but at a reduced rate, driven more by survival under constraint than by diversification. Life persists not as a dynamic, expanding system, but as a collection of enduring lineages resisting extinction. Eventually, even microbial life approaches its limits. Temperature thresholds are crossed beyond which complex biomolecules lose stability. DNA and proteins degrade more rapidly than they can be repaired. Cellular membranes lose integrity. The chemical foundations of life become increasingly difficult to maintain. The final stages of Earth's biological history are not marked by a single extinction event. Instead, they consist of a prolonged decline, stretched across tens to hundreds of millions of years. Life fades unevenly, disappearing from one environment while persisting in another, until only the most extreme niches remain viable. This long goodbye underscores an important truth about life in the universe. Life is not guaranteed permanence, even on planets where it flourishes for billions of years. It exists within constraints imposed by physics and chemistry. When those constraints shift beyond certain limits, life responds by adapting, retreating, or ending. Earth's biological history, viewed in deep time, is therefore finite. The same processes that allowed life to arise and diversify also ensure that it will eventually face conditions incompatible with its continued existence. This outcome does not reflect failure or fragility, but the natural consequence of a changing planetary environment. The end of widespread life does not mean the end of planetary activity. Earth remains geologically dynamic. Volcanoes continue to erupt. Tectonic plates continue to move. The planet's interior remains warm, driven by radioactive decay and residual heat from formation. These processes persist long after biology fades. From a cosmic perspective, Earth's era of abundant life represents a phase, not a permanent state. It occupies a window in deep time defined by a balance between solar energy, atmospheric composition, and surface conditions. As that balance shifts, the window closes. 1 billion years into the future, Earth is not lifeless in a dramatic sense. It is quieter, simpler, more constrained. Life, if it remains at all, exists in isolated pockets, sustained by chemistry rather than sunlight, endurance rather than growth. This transformation does not occur abruptly or violently. It unfolds gradually, guided by the same physical laws that govern the present. The decline of life is not sudden extinction, but a long retreat in the face of changing conditions. As Earth continues along this path, the planet's appearance changes. Landscapes once shaped by biological activity become dominated by physical and chemical processes alone. Soils lose organic content. Colors fade. Surface features become defined by erosion, mineral deposition, and thermal stress rather than growth and decay. The story of life on Earth, when viewed across deep time, is both extraordinary and transient. It demonstrates the capacity of matter to organize itself into complex, self-sustaining systems under favorable conditions. It also demonstrates the inevitability of change when those conditions evolve. With the biosphere diminished and Earth entering a quieter phase, the influence of other long-term processes becomes more apparent. Among these is the slow, steady relationship between Earth and its nearest celestial companion. As life recedes, the Moon's gradual departure continues, subtly reshaping the planet's dynamics. The next stage of this journey follows that distant companion and the long-term consequences of its slow retreat. The Moon has accompanied Earth for more than 4 billion years, shaping the planet in ways that are often overlooked. Its presence influences tides, stabilizes Earth's axial tilt, and subtly affects the rhythm of days and nights. Now, while the Moon appears fixed in the sky on human timescales, it is slowly moving away from Earth, a process driven by the transfer of energy through tidal interactions. This gradual separation began soon after the Moon's formation. As Earth rotates, its oceans respond to the Moon's gravitational pull, forming tidal bulges that are slightly misaligned with the Moon's position. Earth's rotation carries these bulges ahead of the Moon, and the gravitational interaction between them transfers angular momentum from Earth to the Moon. As a result, Earth's rotation slows, and the Moon gains energy, moving into a higher orbit. The rate of this outward drift is small, measured in centimeters per year. Over human lifetimes, the change is imperceptible. Over millions of years, it becomes measurable. Over 1 billion years, it reshapes the Earth-Moon system in significant ways. By that time, the Moon will be tens of thousands of kilometers farther away than it is today. As the Moon recedes, its gravitational influence on Earth weakens. Tidal forces decrease in strength, leading to lower tides across the planet. The dramatic tidal ranges seen in some coastal regions today become less pronounced. Over deep time, this change affects coastal erosion, sediment transport, and the mixing of ocean waters. Tides play an important role in distributing nutrients within the oceans. They help drive circulation in shallow seas and coastal regions, supporting biological productivity. As tidal forces weaken, these processes become less effective. Combined with the warming and thinning of the oceans, reduced tidal mixing further diminishes marine ecosystems. The slowing of Earth's rotation has additional consequences. As angular momentum is transferred to the Moon, Earth's day lengthens. 1 billion years into the future, a day on Earth will be several hours longer than it is today. The transition is gradual, unfolding over millions of years, but it alters the planet's daily rhythm. Longer days influence atmospheric circulation. With more time spent in daylight and darkness during each rotation, temperature contrasts between day and night increase in some regions. These contrasts affect wind patterns, cloud formation, and heat transport around the planet. While Earth's climate is already undergoing major changes due to solar brightening, the lengthening day adds another layer of complexity. The Moon also plays a stabilizing role in Earth's axial tilt. Thus, the angle at which the planet's rotational axis is inclined relative to its orbit around the Sun. This tilt determines the strength of seasons. The Moon's gravitational influence helps prevent large, chaotic variations in this angle. As the Moon moves farther away, this stabilizing effect weakens. Over hundreds of millions of years, Earth's axial tilt becomes more susceptible to perturbations from other planets, particularly Jupiter and Saturn. While extreme variations are unlikely within the next billion years, the potential range of tilt increases. Seasonal patterns may become less predictable, contributing to long-term climate variability. As the moon recedes, eclipses become less frequent and eventually disappear. The moon's apparent size in the sky shrinks, no longer large enough to cover the sun completely. Total solar eclipses, which require a precise alignment of apparent sizes, become a phenomenon of the past. The sky loses one of its most dramatic displays. The weakening of tidal forces also affects Earth's interior. Tidal friction contributes a small amount of heat to Earth's crust and mantle. As this source diminishes, the planet relies more heavily on internal radioactive decay and residual heat for geological activity. While this change is subtle, it influences long-term tectonic and volcanic processes. The Earth-Moon system continues to evolve toward a state of tidal locking, in which Earth's rotation period matches the Moon's orbital period. In this distant future, the same side of Earth would always face the Moon, just as the same side of the Moon faces Earth today. However, this outcome lies far beyond the 1 billion-year mark and will not be reached before other transformative events intervene. Even within the next billion years, the separation between Earth and the Moon becomes a defining feature of the planet's future environment. Nights grow darker as the Moon's brightness diminishes with distance. Its influence on cultural and biological rhythms, already weakened by environmental changes, fades further. The Moon's retreat does not cause sudden disruption. It is a background process, unfolding steadily alongside the Sun's evolution and Earth's climatic transition. Its effects accumulate quietly, reinforcing trends already in motion rather than initiating new ones. As Earth becomes warmer and drier, the diminishing influence of the Moon contributes to a sense of planetary quiet. The forces that once shaped coastlines, regulated rotation, and stabilized seasons grow less pronounced. Earth becomes increasingly dominated by solar input and internal dynamics. The long relationship between Earth and the Moon illustrates how planetary systems evolve through the slow exchange of energy and momentum. No external force is required to drive this change. It emerges naturally from gravity and motion acting together over immense spans of time. 1 billion years into the future, the Moon still orbits Earth, but it does so from a greater distance, exerting a gentler pull. Its presence remains, but its role is reduced. Earth continues forward, carrying the imprint of this ancient partnership even as its influence wanes. As the Moon drifts away, Earth's future becomes increasingly shaped by broader solar system dynamics. The fading influence of its nearest companion makes the gravitational relationships with other planets more significant. Among these, the massive outer planets play a quiet but important role in maintaining long-term orbital stability. The next stage of this journey turns outward, examining how the wider solar system continues to evolve as Earth enters a quieter phase of its existence. As Earth continues forward into deep time, the planet's surface grows increasingly quiet. The processes that once animated its landscapes, flowing rivers, shifting forests, migrating animals, become rare or disappear entirely. What remains is a world shaped primarily by physical forces rather than biological ones. A planet where change still occurs, but without the presence of complex life to respond to it. With oceans no longer stable and life greatly diminished, erosion slows dramatically. On present-day Earth, plants anchor soil, roots break rock, and microorganisms drive chemical reactions that reshape the surface. In the future Earth, these biological contributions are largely absent. Without vegetation, wind becomes the dominant agent of surface change, carrying fine sediments across vast distances and sculpting rock into smooth, wind-polished forms. Temperature extremes intensify as the moderating influence of oceans and atmosphere weakens. Days grow hotter, nights colder. Without abundant water vapor and cloud cover to distribute heat, surface conditions fluctuate more sharply. Rocks expand and contract with daily temperature cycles, slowly fracturing and breaking apart through thermal stress rather than chemical weathering. Volcanic activity continues beneath the surface. Earth's interior remains warm, driven by radioactive decay and residual heat from planetary formation. Volcanoes erupt intermittently, releasing gases into the atmosphere and depositing fresh layers of rock. These eruptions are not coordinated or dramatic on a planetary scale. They occur sporadically, punctuating long periods of relative stillness. Tectonic plates continue their slow motion, though the pace of plate tectonics may decline as internal heat gradually dissipates. Mountain ranges erode and collapse over tens of millions of years, not through rainfall and vegetation, but through wind, gravity, and rare thermal cracking. Landscapes flatten, sharp features soften, relief diminishes. The atmosphere thins as water vapor escapes to space, and chemical reactions alter its composition. As without a robust biosphere to regulate gases, the balance shifts. Oxygen levels drop further. Carbon dioxide fluctuates depending on volcanic outgassing and mineral reactions. The air becomes less capable of supporting complex chemical cycles. Dust becomes a defining feature of Earth's surface environment. Fine particles generated by erosion accumulate in vast plains and basins. Winds transport this dust around the planet, occasionally lofting it high into the atmosphere. These dust layers influence surface temperatures by reflecting some sunlight while trapping heat near the ground. The sky above this future Earth appears different. With fewer clouds and less atmospheric scattering, the sun shines more harshly during the day. The sky may take on deeper hues, influenced by changes in atmospheric composition and density. At night, when the stars appear sharper and more numerous, unobscured by moisture or light pollution. The moon, now farther away, appears smaller in the sky. Its light is weaker, casting fainter shadows. Tides are minimal, and the connection between Earth and its companion feels distant. The rhythmic influence the moon once exerted on Earth's surface has largely faded. Despite the silence, Earth is not static. Subtle changes continue to unfold. Impact events still occur as asteroids occasionally collide with the planet. Without oceans and dense vegetation to erase these scars, impact craters persist for long periods, accumulating as visible records of time passing. Chemical processes continue in the absence of life. Minerals oxidize, react, and transform under heat and pressure. Salts crystallize as remaining water evaporates from shallow basins. Rocks slowly alter their composition through exposure to radiation and temperature extremes. Earth's magnetic field may weaken or fluctuate over deep time as the planet's core cools. While this process is uncertain, changes in the magnetic field influence how solar wind interacts with the atmosphere. Increased exposure to charged particles further alters atmospheric chemistry and contributes to gradual atmospheric loss. The planet's rotation continues to slow as tidal interactions persist, though at a reduced rate due to the moon's distance. Days lengthen further, stretching the cycle of heating and cooling across the surface. The concept of a day remains, but its significance diminishes in a world without biological rhythms tied to light and darkness. In this quiet Earth, the markers of former life remain as geological traces. Fossilized structures, altered sediments, and unusual chemical signatures are preserved in rock layers. These records persist long after life itself has faded, embedded in the planet's crust as evidence of a once active biosphere. The absence of life does not imply emptiness. Physical processes continue to operate, governed by the same laws that shaped the planet from its beginning. Energy flows from the sun to the surface, from the interior to the crust, and from the planet to space. Matter cycles slowly, even without biological mediation. From a distant perspective, Earth still appears as a planet orbiting the sun, reflecting light and following a stable path. Yet its character has changed. It is no longer defined by oceans and life, but by rock, dust, heat, and time. This silent Earth represents a transition rather than an endpoint, and it is a phase in the planet's long history, shaped by the gradual accumulation of changes initiated long before. The absence of noise, motion, and life does not signal completion, but continuity under new conditions. As Earth grows quieter, the focus of change shifts outward. The planet's fate becomes increasingly tied to the broader evolution of the solar system. While Earth settles into relative stillness, the sun and the planets continue their slow progression through time. The next stage of this journey moves beyond Earth's surface, examining how the wider solar system evolves as billions of years pass and the sun advances toward a new phase of its existence. While Earth settles into relative quiet, the solar system continues its slow evolution. The planets do not remain frozen in their present arrangement. They move, interact, and respond to gravitational forces that operate continuously over immense spans of time. These changes are subtle and gradual, but over hundreds of millions to billions of years, they reshape the structure and behavior of the entire system. Planetary orbits are governed primarily by gravity, following predictable paths described by physical laws. On short timescales, these orbits appear stable and unchanging. On deep timescales, however, small gravitational interactions accumulate. The combined influence of planets on one another introduces slow variations in orbital shapes, distances, and orientations. The inner planets experience these changes most strongly. Mercury, closest to the Sun, occupies an orbit that is particularly sensitive to gravitational perturbations. Over long periods, Mercury's orbital eccentricity varies, and sometimes becoming more elongated, while catastrophic instability remains unlikely within the next billion years. Mercury's path illustrates how even seemingly stable systems evolve gradually. Venus continues along its dense, hot trajectory, already far removed from conditions that could support life. As solar radiation increases, Venus's atmosphere becomes even more extreme. Surface temperatures rise further, and any remaining geological processes accelerate under intense heat. Venus remains a powerful example of how planetary environments diverge under different conditions, even within the same solar system. Mars, by contrast, remains cold and dry. Its thin atmosphere offers little protection or insulation. As the sun brightens, Mars receives more energy, but not enough to restore thick oceans or a dense atmosphere. Instead, minor warming occurs, potentially increasing sublimation of polar ice and altering surface chemistry. These changes are limited and do not return Mars to a habitable state. The asteroid belt, located between Mars and Jupiter, continues to evolve through collisions and gravitational interactions. Over time, asteroids fragment, merge, or are ejected from stable orbits. Some are sent inward toward the Sun, others outward toward the outer solar system. These processes occur slowly, shaping the distribution of small bodies without dramatic upheaval. Jupiter remains the dominant gravitational presence in the solar system, aside from the Sun. Its immense mass acts as an anchor, stabilizing many orbital relationships while also reshaping others. Jupiter's gravity influences the paths of asteroids and comets, capturing some into long-term orbits and redirecting others away from the inner planets. Saturn, Uranus, and Neptune continue their slow motion around the Sun, largely unchanged in appearance. Their atmospheres and internal structures evolve subtly as internal heat dissipates and solar input changes. Rings around these planets may thin or disperse as particles collide, fall inward, or escape over long timescales. Beyond Neptune, the distant regions of the solar system remain populated by icy bodies in the Kuiper Belt and Oort cloud. These objects orbit far from the Sun, where changes in solar brightness have little immediate effect. Their motion is influenced primarily by passing stars, galactic tides, and the collective gravitational field of the Milky Way. Over hundreds of millions of years, the close stellar encounters alter the outermost regions of the solar system. Passing stars perturb the orbits of distant objects, occasionally sending comets inward or ejecting them into interstellar space. These interactions are rare but cumulative, contributing to the slow reshaping of the solar system's outer boundaries. The Sun itself moves through the Milky Way, completing a galactic orbit roughly every 225 million years. 1 billion years into the future, the solar system will have completed several such orbits, passing through different regions of the galaxy. Each region presents a slightly different gravitational environment, influencing the distribution of distant objects. Despite these changes, the solar system remains largely intact. The major planets continue to orbit in stable configurations. No sudden rearrangements occur. Stability persists not because change is absent, but because the forces involved operate gradually and within constrained limits. The aging of the solar system is marked by a shift from formation and growth to maintenance, then decay. Early in its history, collisions were frequent and energetic. Over time, the system settles. Large impacts become rarer. Orbits smooth out. Energy dissipates. This gradual quieting mirrors the changes occurring on Earth. Just as the planet transitions from a biologically active world to a quieter geological one, the solar system moves from a dynamic, collision-rich environment to a more sedate configuration dominated by long-term gravitational balance. Yet, even in this quieter state, motion never ceases. Planets continue to circle the Sun. Moons continue to orbit their planets. Small bodies continue to drift, collide, and disperse. The solar system remains a living system in the sense that it evolves, responds, and changes over time. The influence of the outer planets becomes increasingly important as inner planetary environments degrade. Jupiter and its companions act as long-term regulators, shaping the flow of material and energy through the system. Their presence contributes to the overall stability that allows the solar system to persist over billions of years. As time advances, the focus of change shifts gradually away from individual planets and toward larger-scale processes. The Sun's evolution becomes the dominant factor shaping the future, while planetary interactions play supporting roles. The system moves steadily toward a new phase defined by stellar aging rather than planetary activity. This stage of the journey through deep time highlights the resilience of gravitational systems. Even as conditions change and environments degrade, the underlying structure remains. The solar system endures, bound together by gravity and governed by physical laws that operate with quiet consistency. With the planets continuing their patient motion and the Sun slowly evolving, attention turns naturally to the most massive influence within the system. Jupiter's role as a stabilizing presence becomes more apparent as time passes. The next stage explores how this giant planet continues to shape the solar system's long-term behavior, acting as both guardian and sculptor as billions of years unfold. Among all the planets in the solar system, Jupiter occupies a unique position. Its mass exceeds that of all the other planets combined, giving it a gravitational influence that extends far beyond its immediate surroundings. As the solar system ages and the inner worlds grow quieter, Jupiter's role becomes increasingly prominent. It does not change rapidly or dramatically. Instead, it maintains a steady presence, shaping the system through consistency rather than force. Jupiter's gravity dominates the region beyond the asteroid belt. Small bodies that wander into this zone feel its pull strongly, their paths bent and reshaped. Some are captured into stable orbits, becoming moons or Trojan asteroids. Others are redirected, sent inward toward the sun or outward into deep space. These interactions occur continuously, regulating the flow of material through the solar system over immense spans of time. The asteroid belt bears clear evidence of Jupiter's influence. Gaps within the belt correspond to orbital resonances where Jupiter's repeated gravitational tugs destabilize asteroid paths. Over hundreds of millions of years, these resonances clear regions of material, shaping the belt into its present form. This process continues slowly, maintaining a dynamic equilibrium rather than allowing unchecked accumulation or collapse. Jupiter's influence extends to comets originating in the distant reaches of the solar system. Long-period comets from the Oort cloud and shorter-period comets from the Kuiper belt often encounter Jupiter as they move inward. These encounters alter their trajectories, sometimes capturing them into shorter orbits, sometimes ejecting them entirely from the solar system. In this way, Jupiter acts as a gatekeeper, controlling how material moves between the outer and inner regions. As the sun brightens and Earth's environment deteriorates, Jupiter's role remains largely unchanged. Its internal structure continues to generate heat through slow contraction, sustaining powerful storms and a strong magnetic field. These features persist because Jupiter's immense mass allows it to retain energy over billions of years. While the inner planets experience increasing instability, Jupiter remains a constant presence. Jupiter's moons continue their slow evolution under its gravitational influence. Tidal interactions persist, though their effects change as internal heat dissipates and orbital distances adjust. Io's volcanic activity gradually declines as energy sources weaken. Europa's subsurface ocean, if it still exists at this time, becomes increasingly isolated as surface conditions and internal dynamics change. Ganymede and Callisto remain comparatively stable, preserving ancient features over long periods. The giant planet's magnetic field continues to interact with the solar wind, creating a vast magnetosphere that shields its moons from charged particles. This magnetic environment evolves slowly as Jupiter's rotation and internal processes adjust. Despite gradual changes, the magnetosphere remains one of the most powerful structures in the solar system. Jupiter's stability has broader implications for the solar system's future. By maintaining gravitational order in the outer regions, it reduces the likelihood of large-scale orbital disruptions. The presence of such a massive planet dampens chaotic interactions that might otherwise destabilize smaller bodies. And this stabilizing effect becomes increasingly important as the system ages and external perturbations accumulate. Over deep time, the solar system encounters passing stars and molecular clouds as it orbits the Milky Way. These encounters introduce gravitational disturbances, particularly in the distant outer regions. Jupiter's mass helps buffer the inner system against some of these effects, absorbing and redistributing gravitational energy in subtle ways. Despite its stabilizing role, Jupiter is not a guardian with intent. It does not protect specific planets or prevent all impacts. Its influence is impartial, governed by gravity alone. Some objects are deflected away from the inner system, while others are redirected inward. Over long periods, however, the net effect contributes to a more ordered system. As Earth becomes increasingly inhospitable, Jupiter's presence underscores a contrast within the solar system. While terrestrial planets lose water, atmosphere, and biological activity, Jupiter remains largely unchanged in character. Its storms continue to churn. Its bands and zones persist. Its massive bulk resists the kinds of transformations affecting smaller worlds. This contrast highlights the role of mass in planetary evolution. Larger bodies change more slowly, retaining heat and structure over longer timescales. Jupiter's size grants it resilience, allowing it to outlast the dynamic phases of smaller planets. In deep time, mass becomes a form of stability. Jupiter's orbit itself remains remarkably consistent. While minor variations occur due to interactions with other planets, the overall path around the Sun is stable. This consistency contributes to the long-term order of the solar system, anchoring the architecture established billions of years earlier. As the Sun continues toward later stages of its evolution, Jupiter's fate becomes increasingly tied to that of its star. The planet will eventually respond to changes in solar mass and luminosity, adjusting its orbit slightly as the Sun loses mass in distant future phases. For now, however, Jupiter continues its long watch, largely unaffected by the gradual brightening that so profoundly alters the inner planets. The presence of Jupiter serves as a reminder that not all parts of a planetary system evolve at the same pace. While Earth's surface transforms and life recedes, Jupiter endures, governed by slower processes and deeper reservoirs of energy. Its role as a gravitational anchor persists across billions of years. As this chapter of the journey concludes, attention begins to shift once more. The stability Jupiter provides allows the solar system to persist as the Sun advances towards old age. The next stage focuses on the Sun itself, examining how its continued evolution begins to influence the entire system more dramatically, setting the stage for transformations that will eventually affect even the giant planets. As the solar system continues forward through deep time, the Sun remains the central driver of change. Although it still appears stable 1 billion years into the future, its internal structure is steadily evolving. The Sun's long period of balance, sustained by hydrogen fusion in its core, is not endless. In each moment of energy production alters the composition of the core, slowly guiding the star toward a fundamentally different state. At the Sun's center, hydrogen fusion continues to convert mass into energy. Over time, the proportion of helium increases as hydrogen is consumed. Helium, being denser, settles toward the core's center, while hydrogen fusion becomes confined to a gradually shrinking region. This redistribution changes the way energy flows inside the star, increasing pressure and temperature at the core. As the core contracts under its own gravity, temperatures rise further. Higher temperatures increase the rate of nuclear fusion in the surrounding layers. This additional energy pushes outward, causing the Sun's outer layers to expand slightly. Even at this early stage, the Sun begins to show subtle signs of aging, growing incrementally larger and more luminous. These changes occur gradually, unfolding over hundreds of millions of years. There is no sudden transition from youth to old age. Instead, the Sun's behavior shifts continuously, with each stage blending into the next. From a human perspective, the Sun still appears constant. From a stellar perspective, it is steadily advancing along a predetermined path. As solar luminosity increases, the balance of forces within the solar system adjusts. planets respond to the changing gravitational and radiative environment. Orbits remain largely stable, but energy inputs increase. The inner planets, already stressed by rising temperatures, move further away from conditions that could support surface stability. The Sun's expansion at this stage is modest, not yet approaching the dramatic swelling of the red giant phase. However, even slight increases in size and brightness have consequences. Solar radiation intensifies across the inner solar system, accelerating atmospheric loss and surface transformation on terrestrial planets. The Sun's internal evolution also affects its magnetic activity. Changes in convection patterns and energy transport alter the behavior of magnetic fields generated within the Sun. While solar cycles continue, their characteristics may shift subtly over long timescales, influencing the intensity and frequency of solar wind emissions. Solar wind plays a role in shaping planetary atmospheres. Charged particles streaming outward from the Sun interact with planetary magnetic fields and atmospheres, gradually stripping lighter elements from worlds without strong magnetic protection. As the Sun evolves, the cumulative effect of solar wind exposure becomes increasingly significant for smaller planets. Earth, already weakened by atmospheric loss and declining magnetic shielding, becomes more vulnerable to this ongoing erosion. The atmosphere thins further as particles escape to space. Without biological processes to replenish gases, losses accumulate steadily. The Sun's aging also affects the distribution of mass within the solar system. Although mass loss from the Sun remains minimal at this stage, even small reductions in solar mass slightly weaken its gravitational hold. Over long periods, planetary orbits expand outward by small amounts in response. These changes are subtle but measurable on deep time scales. Jupiter and the other giant planets are less affected by increased solar radiation, but they are not entirely immune. Their upper atmospheres respond to higher energy input, expanding slightly and altering chemical reactions. These changes remain confined to the outer layers and do not significantly affect their overall structure. Beyond the planets, the solar system's outer regions continue to experience the combined influence of solar evolution and galactic motion. Distant objects respond primarily to gravitational forces, but changes in solar radiation still influence surface chemistry on icy bodies, altering their composition over long timescales. The Sun's progression toward old age represents a shift in the balance between stability and change. For billions of years, the Sun's output supported relatively stable planetary environments. As hydrogen fusion advances, this stability gives way to a slow but persistent trend toward greater luminosity and internal complexity. This phase of the Sun's life illustrates an important principle of stellar evolution. Stars do not remain fixed in a single state. Even during long periods of apparent calm, they are moving steadily toward transformation. The processes that make stars reliable sources of energy also ensure that they will eventually change in ways that reshape their planetary systems. From the perspective of deep time, the Sun's aging is neither abrupt nor catastrophic. It is a continuation of processes that began at its formation. The energy released today follows the same physical rules that will govern its behavior far into the future. The difference lies in cumulative effects rather than sudden transitions. 1 billion years into the future, the Sun stands at a midpoint between its past and its more dramatic future. It has not yet reached the stage where its expansion threatens the orbits of planets. However, the direction of change is clear. The Sun is moving steadily toward a phase where its influence will become more disruptive. This understanding frames the next stage of the solar system's evolution. As the Sun continues along its path, the inner planets face increasing instability. Their surfaces and atmospheres respond to intensifying radiation and gradual gravitational shifts. The consequences of the sun's aging extend outward, setting the stage for changes that will eventually affect the entire system. With the sun's future trajectory established, attention turns to the planets most directly affected by its evolution. The inner worlds, already transformed by rising temperatures, now face further challenges as solar energy continues to increase. The next stage examines how these planets respond as the sun advances toward later phases of its life, reshaping the solar system from the inside out. As the sun continues its slow evolution, the inner planets experience the most immediate and profound consequences. Their proximity to the star places them directly in the path of increasing radiation and changing gravitational conditions. Each inner planet responds according to its size, composition, and existing environment, revealing how small differences in planetary properties lead to vastly different outcomes over deep time. Mercury, closest to the Sun, exists in an environment already defined by extremes. Its surface temperatures fluctuate dramatically between day and night, and its tenuous atmosphere offers little protection. As solar luminosity increases, these extremes intensify. Surface materials heat beyond their previous limits, accelerating chemical reactions and physical weathering. Mercury's weak gravity and minimal atmosphere allow solar wind to strip away remaining surface volatiles, leaving a world increasingly dominated by exposed rock and metal. Mercury's orbit, sensitive to gravitational perturbations, becomes slightly more eccentric over long timescales. While outright orbital instability remains unlikely within the next billion years, small variations in distance from the Sun amplify temperature differences. These fluctuations further stress the planet's surface, contributing to cracking, sublimation of any remaining volatile compounds, and gradual reshaping through thermal processes. Venus follows a different path. Already enveloped in a dense atmosphere and extreme greenhouse conditions, Venus experiences further intensification as the sun brightens. Surface temperatures rise even higher, pushing chemical reactions toward new regimes. The thick atmosphere becomes more energetic, driving faster circulation and altering cloud dynamics. While Venus remains structurally intact, its environment grows increasingly hostile, moving further away from any possibility of surface stability. The atmosphere of Venus also evolves chemically. Increased solar radiation enhances photochemical reactions in the upper atmosphere, breaking apart molecules and driving escape processes. Although Venus's gravity retains much of its atmosphere, gradual losses occur over long timescales. These changes subtly alter atmospheric composition, though the planet remains dominated by heat and pressure. Earth, once the most temperate of the inner planets, now occupies an intermediate state. With oceans diminished and life largely absent, Earth resembles a transitional world rather than a living planet. Solar radiation continues to strip away lighter atmospheric components, thinning the atmosphere further. Surface temperatures rise beyond levels that allow liquid water to persist even in isolated regions. As Earth's atmosphere thins, surface conditions become more extreme. Without dense air to distribute heat, temperature contrasts sharpen. Regions exposed to direct sunlight experience intense heating, while shaded or nighttime regions cool rapidly. This pattern reinforces physical weathering and accelerates the breakdown of surface materials. Mars, farther from the Sun, experiences more modest changes. Increased solar energy slightly warms its surface, but not enough to restore a thick atmosphere or stable liquid water. Any ice near the surface sublimates more readily, contributing to minor atmospheric fluctuations. Mars remains cold and dry, defined by thin air and exposed rock. The differences among the inner planets illustrate how proximity to the Sun magnifies evolutionary divergence. Small variations in distance, gravity, and atmospheric composition produce dramatically different outcomes when sustained over billions of years. The inner solar system becomes a collection of worlds shaped primarily by solar influence, rather than internal complexity. As solar radiation increases, the boundary between inner and outer planetary environments becomes more pronounced. Terrestrial planets grow increasingly inhospitable, while gas giants and distant icy bodies remain comparatively stable. This contrast highlights the protective role distance plays in planetary longevity. The gradual transformation of the inner planets does not disrupt the overall structure of the solar system. Orbits remain stable. Planetary paths continue to repeat. What changes is not motion, but condition. The inner planets lose the features that once made them dynamic and diverse, becoming worlds defined by exposure rather than interaction. Over deep time, the inner solar system transitions from a region of potential habitability to one dominated by extremes. The Sun's increasing output ensures that these planets move steadily away from states that could support surface stability. Their futures are determined not by sudden events, but by the persistent application of energy. As the inner planets settle into these altered states, the solar system's center of activity shifts outward. The focus moves away from terrestrial worlds and toward larger-scale structures and processes. The influence of planetary environments gives way to stellar and galactic dynamics as the primary drivers of change. With the fate of the inner planets increasingly constrained by solar evolution, attention naturally expands beyond the immediate vicinity of the Sun. The solar system does not exist in isolation. It moves through the Milky Way, interacting with a broader cosmic environment that shapes its long-term history. The next stage explores how this galactic context influences the solar system as billions of years pass and the Sun continues its journey through space. The solar system does not exist as a fixed island in space. It is embedded within the Milky Way galaxy, moving along a vast orbit that carries it through changing environments over hundreds of millions of years. As time advances toward and beyond the 1 billion-year mark, this broader galactic context becomes increasingly relevant. While the planets continue their steady motion around the Sun, the entire system is also traveling through a dynamic cosmic landscape. The Sun orbits the center of the Milky Way at a distance of roughly 27,000 light-years, completing a single galactic revolution approximately every 225 million years. 1 billion years into the future, the solar system will have completed several such orbits. Each pass carries it through different regions of the galaxy, each with slightly different densities of stars, gas, and dust. These variations matter over deep time. In regions where stars are more densely packed, gravitational interactions become more frequent. Passing stars can exert weak but cumulative influences on the solar system, particularly on its outermost regions. The inner planets remain largely unaffected, held tightly by the Sun's gravity. Farther out, however, distant icy bodies respond more readily to these subtle disturbances. Beyond Neptune lies the Kuiper Belt, a broad disk of icy objects orbiting the Sun. Even farther out, yet extending tens of thousands of astronomical units, is the Oort cloud, a vast and diffuse reservoir of comet-like bodies. These regions are only loosely bound to the Sun. Galactic tides and passing stars gradually reshape their structure, nudging objects into new orbits or ejecting them into interstellar space. As the solar system continues its journey around the galaxy, encounters with other stars occur occasionally. Most are distant and brief, producing only minor gravitational effects. Over hundreds of millions of years, however, their influence accumulates. Some encounters send comets inward toward the Sun, increasing the likelihood of impacts on planets. Others remove material entirely, thinning the outer reservoirs. These processes do not destabilize the solar system as a whole. Instead, they slowly modify its outer boundaries, and the distribution of distant objects changes, becoming more diffuse and less structured. The solar system gradually loses material to the interstellar environment, a quiet exchange that unfolds over immense spans of time. The Milky Way itself is not static. Star formation continues in some regions while others grow quieter. Supernovae occur intermittently, releasing bursts of energy and heavy elements into surrounding space. While such events rarely occur close enough to directly affect the solar system, their cumulative effect shapes the galactic environment through which the Sun travels. Radiation levels vary slightly depending on location within the galaxy. As the solar system passes through spiral arms or regions of higher stellar density, background radiation increases modestly. These variations influence the chemistry of distant, icy bodies and contribute to slow changes in surface composition. The inner planets remain shielded by distance and solar influence, but the outer regions respond more sensitively. The solar system's motion through the galaxy also alters its orientation relative to galactic structures. Over time, the plane of the solar system tilts slightly relative to the Milky Way's disk. These changes are subtle and have little direct impact on planetary environments, but they reflect the dynamic nature of the system's galactic context. From a broader perspective, the Sun is one of hundreds of billions of stars moving through the Milky Way. Its planetary system is neither central nor unique. As time progresses, the significance of local planetary conditions diminishes in comparison to larger-scale cosmic processes. The solar system becomes one small component in a much larger pattern of galactic evolution. The movement of the solar system through the galaxy also emphasizes the scale of deep time. Events that seem rare or unlikely on human timescales become inevitable when given hundreds of millions of years. Stellar encounters, gravitational perturbations, and gradual material loss are not exceptions. They are expected outcomes of motion through a crowded universe. Despite these influences, the solar system retains its identity. The Sun continues to bind its planets, moons, and smaller bodies together. The architecture established early in its history remains recognizable, even as outer regions evolve and thin. Stability persists, not because change is absent, but because the system is resilient. As the Sun ages, the relative importance of galactic influences grows. Changes within the solar system increasingly reflect not only internal dynamics, but also the broader environment through which it travels. The future of the solar system is shaped as much by its motion through the Milky Way as by the evolution of its central star. Looking outward beyond the solar system provides perspective on scale and context. The fate of planets and stars unfolds within a galaxy that itself is evolving, interacting with neighboring galaxies and changing over cosmic time. The story of Earth and the Sun is part of a much larger narrative. As this journey continues, attention shifts from planetary systems to the structure and behavior of the galaxy itself. The Milky Way, vast and slowly changing, provides the backdrop against which the solar system's future unfolds. The next stage examines how the galaxy evolves over deep time and how its long-term dynamics influence the environment in which stars and planetary systems exist. The Milky Way appears stable when viewed from within, its stars forming familiar patterns that change little over a human lifetime. Yet on deep time scales, the galaxy is in constant motion. Stars orbit its center, spiral arms drift and reform, and vast clouds of gas slowly collapse or disperse. 1 billion years into the future, the Milky Way remains recognizable, but its internal balance continues to evolve. At the galaxy's core lies a supermassive black hole, around which billions of stars move in complex orbits. The influence of this central mass shapes the motion of stars in the inner regions, while farther out, the combined gravity of stars, gas, and dark matter governs galactic rotation. These forces operate continuously, guiding the structure of the galaxy over immense periods of time. Stars are born in dense molecular clouds, where gravity pulls gas together until nuclear fusion ignites. Over time, these clouds are consumed or disrupted by stellar radiation and supernova explosions. As the Milky Way ages, the overall rate of star formation slowly declines. Gas becomes less abundant, locked away in long-lived stars or expelled into intergalactic space. This gradual decline in star formation alters the character of the galaxy. Young, bright stars become less common. Older, cooler stars dominate the population. The galaxy's light shifts subtly toward longer wavelengths as massive, short-lived stars become rarer. Supernovae continue to occur, but less frequently. These explosions play a critical role in redistributing heavy elements, enriching the interstellar medium with the building blocks of planets and life. As their frequency decreases, the pace of chemical enrichment slows. The galaxy enters a quieter phase of evolution. Spiral arms, often perceived as fixed structures, are actually patterns of higher density that move through the galactic disk. Stars pass in and out of these regions as they orbit the center. Over hundreds of millions of years, spiral patterns shift, dissolve, and reform. The Milky Way's appearance changes subtly, though its overall disk-like structure remains intact. The solar system continues its orbit through these evolving structures. Each passage through a spiral arm slightly increases the density of nearby stars and gas, raising the likelihood of close stellar encounters and exposure to higher radiation environments. Over deep time, these repeated passages contribute to gradual changes in the solar system's surroundings. Dark matter, though invisible, plays a dominant role in shaping the galaxy's structure. It forms an extended halo around the Milky Way, influencing how stars and gas move. The distribution of dark matter remains relatively stable over billion-year timescales, providing a gravitational framework that maintains the galaxy's cohesion. The Milky Way does not evolve in isolation. It interacts gravitationally with neighboring galaxies, and particularly smaller satellite galaxies that orbit it. Over time, these satellites are drawn inward, stretched, and eventually absorbed. Streams of stars from these disrupted galaxies become part of the Milky Way's halo, adding to its mass and complexity. 1 billion years into the future, some satellite galaxies that exist today may no longer remain distinct. Their stars will have merged into the Milky Way, contributing to its gradual growth. This process is slow and uneven, unfolding over hundreds of millions of years without dramatic disruption. The galactic disk also thickens over time as stellar orbits become more dispersed. Interactions between stars, molecular clouds, and spiral arms gradually increase the vertical motion of stars, making the disk less sharply defined. The Milky Way becomes slightly puffier, its structure more diffuse. Despite these changes, the galaxy retains its identity. It remains a spiral galaxy, bound together by gravity and dark matter. Its rotation continues, carrying stars and planetary systems along paths that repeat over vast spans of time. From the perspective of deep time, the Milky Way's evolution emphasizes continuity rather than upheaval. There are no sudden collapses or radical transformations within the next billion years. Instead, the galaxy matures, transitioning slowly from a more active state to a quieter one. This maturation affects all stars within the galaxy, including the Sun. As the galactic environment evolves, the solar system experiences changes in radiation exposure, gravitational interactions, and the availability of interstellar material. These influences are subtle, moorings, but they contribute to the broader context of the solar system's future. The Milky Way's deep-time evolution sets the stage for even larger-scale processes. Galaxies themselves are not permanent structures. Over longer periods, they interact, merge, and transform in ways that reshape the universe. While such events lie beyond the 1 billion-year horizon, the slow changes already underway hint at the future direction of cosmic evolution. Understanding the Milky Way in deep time provides perspective on scale and significance. Planetary systems and even stars are temporary components within a much larger, longer-lived structure. The galaxy persists through countless stellar lifetimes, evolving gradually as energy dissipates and matter rearranges. As this exploration of the Milky Way concludes, Otis' attention turns to the interactions that unfold over even greater distances and timescales. The next stage examines how massive objects influence one another through gravity, producing encounters and collisions that take hundreds of millions or billions of years to complete, yet shape the structure of the universe in lasting ways. In the vastness of space, collisions do not resemble the sudden impacts familiar from everyday experience. On cosmic scales, encounters unfold slowly, guided by gravity over millions or billions of years. Objects approach one another gradually, their paths bending long before any contact occurs. What appears violent in outcome is often the result of immense patience rather than speed. Within galaxies, stars move along orbits determined by the combined gravitational pull of billions of other stars. Gas clouds, and dark matter. These orbits are not fixed tracks. Over time, they shift subtly due to gravitational interactions. Most stars pass one another at safe distances, their motions barely affected. Occasionally, however, trajectories align in ways that lead to close encounters. A stellar encounter rarely involves a direct collision. The distances between stars are vast, even in dense regions. Instead, gravity does the work. As two stars pass near one another, their gravitational fields interact, altering velocities and orbital paths. These interactions redistribute energy and momentum, slowly reshaping the structure of star clusters and galactic disks. Over hundreds of millions of years, repeated gravitational encounters gradually change the distribution of stellar orbits. Some stars gain energy and move outward from the galactic center. Others lose energy and drift inward. This process, known as dynamical relaxation, contributes to the slow evolution of galaxies, thickening disks and populating halos with stars scattered from their original paths. In regions where stars are more densely packed, such as globular clusters or galactic centers, interactions occur more frequently. Here, gravitational encounters can be strong enough to eject stars entirely or draw them into tight binary systems. These binaries, once formed, may persist for billions of years, slowly losing energy through interactions with surrounding stars. Binary systems play a central role in some of the most dramatic events in the universe. When two massive objects orbit one another, their mutual gravity binds them into a long-term relationship. Over time, interactions with nearby stars or gas clouds can tighten their orbit, bringing them closer together. This process unfolds gradually, often taking hundreds of millions of years. In some cases, the binary objects are not stars, but remnants such as neutron stars or black holes. These dense objects form from the collapsed cores of massive stars and possess intense gravitational fields. When two such objects become bound, they begin a slow inward spiral, driven by the emission of gravitational waves. Gravitational waves carry energy away from the system, causing the orbit to shrink. This loss of energy is extremely small on short timescales. Over millions to billions of years, however, it becomes decisive. The objects draw closer, orbiting faster as their separation decreases. From a distance, this process is invisible. No light is emitted. No explosion occurs. Space itself carries away the energy through subtle ripples that propagate outward at the speed of light. These waves pass through galaxies, stars, and planets without disruption, leaving only the faintest trace. Eventually, the inspiral reaches a final phase. The two objects orbit each other rapidly, completing many revolutions each second. In this brief moment, lasting only seconds or minutes, the energy release becomes intense. The collision, or merger, produces a powerful burst of gravitational waves, momentarily outshining all other sources in the universe in that form of energy. Despite the dramatic nature of the merger, its effects are localized. Nearby space is disturbed, but distant regions remain unchanged. The universe absorbs the event without interruption, continuing its gradual evolution. And these collisions illustrate an important principle of deep time. Events that appear sudden are often the culmination of processes that unfolded patiently over immense spans. The universe does not rush toward violence. It drifts toward it, guided by gravity and time. Galaxies themselves experience similar slow-motion encounters. When two galaxies pass near one another, their stars rarely collide. Instead, gravitational forces stretch and distort their shapes, pulling out long tidal tails and rearranging stellar orbits. These interactions unfold over hundreds of millions of years, reshaping galaxies without destroying their contents. In the distant future, the Milky Way is expected to merge with the Andromeda Galaxy. This encounter will not be an instantaneous collision, but a prolonged interaction involving multiple close passes and gradual merging. Stars will continue to orbit, largely unaffected individually, while the overall structure transforms. These galactic mergers contribute to the long-term evolution of the universe. They redistribute matter, trigger bursts of star formation in some regions, and feed central black holes. Over deep time, such interactions reduce the number of separate galaxies, producing larger, more massive systems. Throughout these processes, gravity remains the driving force. It operates without preference or urgency, shaping structures through consistent influence rather than sudden intervention. Collisions and mergers are not exceptions to cosmic order, they are expressions of it. Understanding these slow-motion encounters provides context for the future of the solar system. While direct collisions involving Earth are unlikely, the system exists within a galaxy that continues to evolve through gravitational interaction. Over billions of years, the environment around the Sun changes as stars and structures drift, merge, and separate. The concept of collisions unfolding over deep time challenges intuition. It reveals a universe where change is measured not in moments, but in eras. Events that appear catastrophic are often the natural outcome of long-term processes reaching their conclusion. As this stage of the journey concludes, the focus shifts from interactions that reshape structure to trends that alter the universe's overall character. Beyond individual collisions and mergers lies a broader transformation affecting all cosmic systems. The next stage examines how the universe itself grows quieter as energy spreads and star formation slows, marking a gradual transition toward a more subdued cosmic state. As billions of years pass, the universe does not become more chaotic. It becomes calmer. The dramatic events that once defined cosmic history, frequent star formation, intense radiation, and violent interactions, gradually give way to longer periods of quiet. This transition is not sudden or universal. It unfolds unevenly, guided by the slow redistribution of energy and matter across vast distances. In the early universe, gas was abundant and densely packed. Gravity easily pulled material together, forming new stars at a rapid pace. These stars burned brightly and briefly, ending their lives in supernova explosions that enriched space with heavy elements. Over time, however, much of this gas was consumed or locked away in long-lived stars and stellar remnants. As the supply of free gas diminishes, the rate of star formation declines. New stars still form, but less frequently and in fewer regions. The galaxy's brightest, most massive stars become rare. What remains are smaller, longer-lived stars that burn their fuel slowly and steadily. The overall brightness of galaxies decreases as energetic processes become less common. This trend is not confined to a single galaxy. Across the universe, star formation follows a similar pattern. Galaxies mature, using up their available fuel. The universe transitions from a period of rapid construction to one of maintenance and gradual fading. With fewer massive stars being born, supernova explosions become less frequent. These explosions once played a major role in stirring interstellar material, driving turbulence, and triggering new waves of star formation. As they become rarer, the interstellar medium grows calmer. Gas clouds drift quietly and large-scale motion slows. The decline in energetic events affects radiation levels throughout space. High-energy photons become less abundant. Background radiation shifts toward lower energies as the universe expands and cools. The cosmic environment becomes gentler, dominated by long-wavelength light emitted by aging stars. Black holes continue to exist, but their growth slows. In earlier eras, abundant gas and frequent galactic interactions fed central black holes, causing them to shine as quasars. As galaxies settle and gas supplies dwindle, these luminous phases become rare. Black holes persist as massive, silent objects, exerting gravitational influence without dramatic display. The expansion of the universe continues throughout this period. Space itself stretches, increasing the distance between galaxies. While galaxies bound by gravity remain together, isolated systems drift farther apart. Over time, the universe becomes more fragmented, with each galaxy or group of galaxies increasingly isolated from the others. This expansion affects how light travels through space. Photons emitted by distant sources are stretched to longer wavelengths as they cross expanding space. Energy spreads out, becoming more diffuse. Even the most energetic events gradually fade into the background as their signals are diluted by distance and time. The universe's quieting reflects a fundamental physical principle. Energy tends to spread out. Over deep time, concentrated energy sources diminish, and differences in temperature and density smooth out. This process, known as the progression toward equilibrium, governs the long-term behavior of all physical systems. Despite this trend, the universe does not become empty or inactive. Motion persists. Stars continue to orbit galactic centers. Planets circle stars. Black holes influence their surroundings through gravity. The difference lies in intensity rather than existence. Change becomes slower, subtler, and more diffuse. On planetary scales, these cosmic changes may seem abstract, yet they provide the context for all local processes. The future of the solar system, Earth, and even the Sun unfolds within a universe that is gradually losing its capacity for dramatic transformation. As the universe grows quieter, the contrast between early and late cosmic history becomes apparent. What once required little time now requires great patience. Events that were common become rare. Structures that formed quickly now evolve slowly. This quieting also marks a shift in the nature of observation. Signals from distant galaxies take longer to arrive and carry less energy. The observable universe shrinks as more regions move beyond causal contact due to expansion. The cosmic horizon closes in, limiting what can be seen or influenced. The long-term trend toward calm does not erase complexity entirely. It reshapes it. Systems persist, but their evolution stretches across ever longer timescales. Stability replaces dynamism. Endurance replaces growth. This stage of cosmic history prepares the universe for its far future, where processes operate at a pace almost indistinguishable from stillness. The gradual loss of energy and interaction sets the stage for environments defined more by persistence than change. As this exploration continues, attention turns from the broad quieting of the universe to the fate of matter itself. Beyond fading stars and slowing galaxies lies a deeper question about how long structures can endure and what ultimately becomes of the material that composes them. The next stage examines the far future of matter and the limits imposed by physical law. As the universe grows quieter, attention shifts from large-scale structures to the nature of matter itself. Stars fade, galaxies settle, and energetic events become rare, but atoms and particles continue to exist. Their behavior, governed by fundamental physical laws, determines how long structure can persist in an aging universe. Matter appears stable on human timescales. Atoms retain their identity, molecules form and break, and solid structures endure for centuries or millennia. Over deep time, however, even the most stable forms of matter are subject to gradual change. The persistence of matter is not absolute. It depends on conditions, interactions, and the underlying properties of particles. One of the key questions in long-term cosmology concerns the stability of protons. Protons are the building blocks of atomic nuclei, forming the core of every atom heavier than hydrogen. In current observations, protons appear extremely stable, with no confirmed instances of decay. Yet some theoretical models suggest that protons may eventually decay over timescales far exceeding the current age of the universe. If proton decay occurs, its effects are imperceptible on billion-year scales. The half-life proposed by some theories extends beyond 10 trillion years. Within the time frame considered here, matter remains effectively intact. Atoms continue to exist, and the structures formed from them persist, albeit in increasingly inactive environments. Even without proton decay, matter changes through more familiar processes. Radioactive elements continue to decay, releasing energy and transforming into more stable forms. On Earth and other rocky bodies, radioactive decay contributes to internal heat. Over billions of years, this heat source diminishes as unstable isotopes are exhausted. As radioactive heating declines, planetary interiors cool. Geological activity slows. Volcanism becomes less frequent. Tectonic motion weakens. While these processes do not stop entirely within a billion years, their influence becomes less pronounced. Planets transition from dynamic interiors to more rigid, slowly changing structures. At the atomic level, chemical reactions continue as long as energy and reactants are available. On future Earth, these reactions become increasingly limited by temperature extremes and the absence of liquid water. Chemical change persists primarily through solid-state reactions and interactions driven by heat and radiation. Radiation remains a persistent influence. Even as stars fade, background radiation permeates space. Cosmic rays, though less frequent, continue to interact with matter. Angst is causing occasional atomic disruptions. Over long periods, these interactions alter surface materials, breaking chemical bonds and creating new compounds. In space, dust grains and icy bodies undergo slow transformation under radiation exposure. Molecules are broken apart and recombined. Surfaces darken and chemically evolve. These changes occur gradually, driven by constant low-level energy input rather than sudden events. Black holes, among the most extreme forms of matter, persist as long-lived structures. Their influence is purely gravitational. They do not fade in the same way stars do. Over extraordinarily long timescales, black holes may lose mass through a process known as Hawking radiation. However, this effect is negligible on billion-year timescales. Black holes remain effectively permanent features of the universe at this stage. The persistence of matter contrasts with the fading of energy gradients. While atoms remain, the differences that drive change, temperature contrasts, pressure differences, chemical imbalances, become less pronounced. Systems approach equilibrium, not because matter disappears, but because there is less energy available to rearrange it. This shift has implications for complexity. Complex structures require sustained energy flows to maintain organization. As energy becomes more diffuse, maintaining complexity becomes increasingly difficult. Structures persist, but they do so in simpler, more static forms. In this context, the universe's far future is not characterized by sudden dissolution, but by gradual simplification. Matter remains present, but its capacity to participate in dynamic processes diminishes. Change slows, stretching across ever longer timescales. The fate of matter is therefore tied to the fate of energy. As energy spreads out and differences diminish, matter settles into configurations that require minimal maintenance. Rocks remain rocks. Atoms remain atoms. Motion persists, but without urgency. This perspective reframes the concept of an ending. The universe does not abruptly lose its contents. Instead, it transitions toward a state where activity is rare and transformation is slow. Matter endures, even as the conditions that once drove dramatic change fade. Within the 1 billion-year horizon, these processes are only beginning. Matter remains abundant and recognizable. The universe retains its structure, yet the direction of change is clear. Over deep time, a matter moves toward a quieter existence, shaped less by interaction and more by persistence. Understanding the far future of matter provides context for the earlier stages of cosmic evolution. It highlights the continuity of physical law across all timescales. The same principles that govern atoms today will govern them far into the future, even as the environment in which they exist becomes calmer. As this stage concludes, the focus turns from matter itself to the question of observation and meaning. In a universe that grows quieter and simpler, the presence or absence of observers takes on a different significance. The next stage explores time in the absence of witnesses and considers how change unfolds when no one is present to mark it. Beyond this point, understanding the future becomes less certain. The processes described so far follow well-tested physical principles, supported by observation and experiment. What follows moves into a different category of thought. These ideas are not predictions, but possibilities. They are frameworks for thinking about what might occur if known laws continue to operate in ways that theory allows, even where direct evidence remains incomplete. Speculation in science serves a specific purpose. It does not replace observation, but it extends understanding to regimes that cannot yet be tested. In deep time, many outcomes lie beyond direct measurement. the universe becomes a laboratory too large and too slow to observe directly. In this context, speculation is used carefully, constrained by what is already known and always subject to revision. One area of speculation concerns the long-term behavior of information in the universe. Information, in physical terms, is tied to the arrangement of matter and energy. As structures simplify and energy spreads, information becomes harder to preserve in complex forms. Patterns that once required constant energy to maintain gradually dissolve. Some physicists suggest that information is never truly destroyed, only transformed. In this view, even as stars fade and matter disperses, the information encoded in particles and fields persists in altered form. This persistence does not imply consciousness or intention. It reflects the conservation principles embedded in physical law. Another speculative idea involves the role of black holes in information storage. Black holes, despite their apparent simplicity, possess properties that suggest they encode information about the matter that formed them. Over unimaginably long timescales, as black holes slowly lose mass, this information may be released back into the universe in highly scrambled form. These processes, if they occur, unfold over periods far longer than 1 billion years. Within the time frame considered here, black holes remain stable repositories of mass and information. Their relevance lies not in immediate effects, but in their role as endpoints of structure in the universe. Speculation also extends to the nature of complexity in a quiet universe. Complexity arises when energy flows allow matter to organize into patterns that resist equilibrium. As energy gradients weaken, complexity becomes increasingly rare. Some theorists ask whether complexity could re-emerge under different conditions, or whether the universe's trajectory ultimately favors simplicity. There are ideas that suggest transient pockets of complexity could arise even in a fading universe, driven by rare fluctuations or long-lived energy sources. These scenarios are mathematically possible, but statistically unlikely. They do not represent a return to widespread activity, but isolated exceptions within a largely calm cosmos. Another speculative area involves consciousness and its dependence on physical conditions. Conscious systems require stable structures, energy flow, and information processing. As environments grow less dynamic, sustaining such systems becomes more difficult. Whether consciousness can exist in forms vastly different from biological life remains an open question. Some hypotheses explore non-biological substrates for information processing, such as long-lived physical systems capable of slow computation. These ideas remain theoretical and lack empirical support. They are valuable primarily as thought experiments that clarify the constraints imposed by physics. It is important to distinguish between speculation grounded in physical law and imaginative scenarios unconstrained by evidence. The former extends known principles into unfamiliar regimes. The latter belongs to fiction. In exploring deep time, maintaining this distinction preserves clarity and trust. Within 1 billion years, the universe does not undergo radical speculative transformations. Stars still shine. Matter remains structured. Energy gradients persist. The speculative ideas discussed here become relevant only as long-term context, not as immediate outcomes. Speculation helps frame the limits of knowledge. It marks where understanding transitions from confidence to uncertainty. In doing so, it highlights the strength of what is known by contrast. The universe's behavior up to this point is governed by well-established principles that continue to operate reliably. As time advances beyond direct observation, humility becomes essential. Predictions give way to ranges of possibility. The universe may follow one path or another, constrained by law but open in detail. Recognizing this uncertainty is part of scientific understanding, not a weakness. This chapter does not attempt to resolve these questions. It acknowledges them. It places them where they belong, beyond the boundary of current evidence, while keeping them connected to known physics. In this way, speculation remains a tool for exploration rather than assertion. As this reflective pause concludes, attention turns back to what can be described with confidence: the experience of time itself in a universe that continues to evolve, whether observed or not. The next stage examines how change proceeds in the absence of witnesses, and what it means for events to unfold without measurement, memory, or record. As the universe continues forward, a subtle shift occurs that has nothing to do with stars, planets, or matter itself. It concerns observation. For most of cosmic history, change has been accompanied by witnesses: particles interacting, systems responding, structures recording the past through their configuration. But as complexity declines and activity slows, the question arises of what it means for time to pass when there is little left to mark it. Time, in physical terms, does not require observers. It is defined by change, motion, interaction, and transformation. Even in the quietest universe, particles move, fields fluctuate, and gravity continues to operate. Processes persist regardless of whether they are recorded or remembered. The absence of witnesses does not halt the progression of events. Yet without observers, time loses familiar reference points. There are no clocks in the traditional sense, no cycles tied to biology, no memories accumulating. Time continues, but it does so without narrative. Moments no longer connect into stories. They exist only as states following one another according to physical law. In earlier eras, time was marked by rhythm. Days followed nights, seasons followed seasons, generations followed generations. These cycles created structure, repetition, and expectation. In a future universe with fewer dynamic systems, such rhythms become rare or disappear entirely. Time becomes less segmented and more continuous. On a silent Earth, for example, the passage of a day remains defined by rotation, but nothing responds to it. There is no activity that distinguishes morning from evening. Light falls on rock, then darkness returns, without consequence. The cycle persists, but its significance fades. On larger scales, galaxies continue to rotate and drift, but their internal evolution slows. Stars age, but few new ones are born. The difference between 1 million years and the next becomes harder to distinguish. Time stretches, not in duration, but in perceptual meaning. From a physical perspective, this does not represent stagnation. Motion continues. Gravitational systems remain active. Energy flows, however faintly. What changes is the density of events, how much happens per unit of time. As this density decreases, time feels emptier in content, even though it proceeds at the same rate. This concept challenges intuition shaped by short-lived systems. Humans experience time through change, growth, decay, movement, and memory. When change slows, time seems to slow with it, even though it does not. In the far future, the universe does not run out of time. It runs out of novelty. Even without witnesses, the universe continues to explore its allowed states. Particles interact. Rare events occur. Given enough time, even unlikely configurations may arise briefly before dissolving again. These moments are not observed, but they are real, defined by the same laws that governed earlier eras. This raises deeper questions about meaning. Meaning, as humans understand it, arises from relationships, memory, and interpretation. In a universe without observers, meaning is not assigned. Events occur without being framed as significant or insignificant. They simply occur. From the standpoint of physics, this absence of meaning is not a deficiency. It is a return to neutrality. The universe does not require interpretation to function. Its laws operate without intention or awareness. Time flows whether or not it is noticed. The idea of time without witnesses reframes the concept of an ending. There is no final moment when the universe stops. There is no closing chapter marked by silence. Instead, there is a gradual thinning of events until change becomes rare and widely spaced. Within the 1 billion-year horizon, witnesses still exist in the form of active stars, structured systems, and ongoing interactions. The universe remains rich in activity. The concepts explored here point beyond that horizon, offering perspective rather than prediction. By stepping back from familiar measures of time, it becomes possible to view the universe as a system evolving independently of observation. Change is not driven by attention, it is driven by law. The presence of observers is an outcome of certain conditions, not a requirement for time to pass. This understanding brings the journey through deep time to a natural pause. From the present through 1 billion years and beyond, the universe follows a continuous path shaped by energy, matter, and gravity. Events unfold whether they are noticed or not. Structures form, persist, and fade. What remains constant across all these stages is not activity or complexity, but consistency. The same physical principles apply at every moment, from the era of abundant life to the quiet future of fading stars. Time carries these principles forward without pause or preference. This completes the exploration of deep time from a grounded scientific perspective. Not as a story of catastrophe or mystery, but as a steady unfolding of consequences arising from simple rules applied over immense spans. The universe does not hurry. It does not stop. It continues. As this journey through deep time comes to a close, what remains is perspective. The future is not shaped by sudden endings, but by quiet continuations. Stars age, planets transform, galaxies drift, and the universe moves forward according to laws that never pause. 1 billion years from now is not an ending point, but another moment in an unfolding story far larger than any single world. If you found value in exploring the universe at this scale, take a moment to support the channel. Like the video, share it with others who enjoy long-form science and sleep documentaries, and subscribe to continue these deep journeys through space and time. More stories are already forming, written into the fabric of the cosmos, waiting to be explored.